Welcome to this Wine Australia webinar on the Climate Atlas. My name is Sharon Harvey. I'm a Research and Development Program Manager here at Wine Australia. And alongside me on your screen, you will see Dr. Rebecca Harris and Dr. Tom Remini, who delivered the project that brought us the Climate Atlas, which we'll discuss today, and digging a little bit deeper into the regions in SA Central in South Australia. So mainly McLaren Vale, Adelaide Hills and Langhorne Creek areas. So we'll be having a 30 to 45 minute presentation followed by a Q&A session. On your screen you should see a chat tab, and feel free to enter any questions that you have as the presentation goes on via that chat. We'll curate those questions in the background and they'll form the basis of the Q&A session at the end. In the control room with me, I have our Extension Officer, Belinda Bramley, and she has ironed out the technical difficulties which we've already encountered. Fingers crossed, it's all good. Just a reminder too that this presentation is being recorded and will be available on the Wine Australia website at its conclusion. So I think that is all from me. Without further ado, I'll pass over to Beck and Tom for the presentation. And just a reminder that the intention for today is to give you an overview of the Atlas, a feel for why we did the work in the first place, and to empower you to make some decisions for yourselves and for your region going forward to adapt to the climate change that we're going to talk about today. So I'll hand over and see you all at the other side.
Thanks, Sharon, and thanks to everyone for joining us. Tom, I still can't see your screen, but I'll just start with the introduction. And there you go. Thanks, I can see it now. So, as I said before, Tom and I were responsible for producing the Wine Atlas along with the Climate Futures team. And the project started with Wine Australia in about 2015, recognising that climate change is going to pose significant challenges to this sector. And that's the case for all sectors around the country and around the world, because we're looking at temperature increases of 3.5 or 4 degrees relative to 1961 to 1990 by the end of the century, if we continue under the high emission scenario, which is the scenario that we're currently tracking slightly above. So the project was Australia's Wine Future, and it was funded by Wine Australia. And the focus was to look at the impacts of climate variability as well as long-term trends in climate on the wine industry. So it was a collaborative research project that brought together about 15 researchers from a range of disciplines, including climate modellers, climate scientists, viticulturalists, and people with expertise in adaptation. So what the aim was to provide Australia-wide climate information that was tailored for the wine industry and at a fine enough resolution to inform targeted adaptation responses. As Sharon said, with the intention of providing a tool so that you guys can start to make and plan for your futures based on good climate information. So really good climate information is really vital for making those decisions, to be making them informed, so that you can start to make those plans at the short, medium and longer term timescales. So that's where the Atlas comes in, the basis of the good information, so that we can provide grape growers and winemakers information about the climate change that we've already experienced and the trends that we're expecting into the future. So what's in the Atlas? So basically it's a summary of changes in climate that we've already seen across the wine regions and the changes that we're expecting going forward out to the end of the century. So the summaries are based on the most up-to-date climate information at the farmers resolution that is currently available across Australia. So we've got resolutions ranging from 5 kilometres to 10 kilometres, and we'll see in the next slide or two which regions are which. So we have a separate section for every geographic indicator across the country, describing changes to temperature, heat accumulation, extreme events in both heat and cold, rainfall and aridity. So there are maps that also show variability both within the regions and across the regions, and each of those separate sections has 5 separate pages that lays out graphically the sorts of changes that we're expecting. So here I've got in the smaller text that list of indices that we have developed for the Atlas. Obviously, we can't go through all of those today, but Tom's going to take you through some of the details in the major indices. And the indices were chosen after quite extensive conversations with people in the wine industry, because we were trying to make sure that those indices were usable. We wanted to include accepted indices that are currently widely used and relevant to growing grapes. So if you go to the next slide, Tom. So you can see here that this shows us the range in spatial resolution that the dynamically downscaled climate model gives us. So we've got 5 kilometres over the central part of that figure in southeastern Australia, widening out to about 10 kilometres over Tasmania, and the rest of the country is at 50 kilometres, but which were then statistically downscaled to 5 kilometres. So we used 6 global climate models that were dynamically downscaled by the CSIRO part of the research team. And in the Atlas, we show all of those 6 climate models. So we show the range in values that are provided by those 6 climate models. I guess, so this is just showing you what a climate model actually looks like. You can see that they're dynamic beasts. They're really complex models. They're not just a line on a graph. Global climate models typically have a horizontal resolution of between 50 and 250 kilometres. They have about 10 to 20 vertical layers in the atmosphere. So here you can see we've got 2 layers of cloud, an upper layer and a lower layer. This is surface temperature, and so you can see that there's an interaction between the land surface and the atmosphere. So it's not just a matter of a statistical relationship. These are dynamic models that incorporate the regional climate processes that are happening in our regions of interest. So this is the output from the dynamically downscaled regional climate model, which gives us that 5 kilometre resolution, and also 1 hour time steps, which is what you're seeing here. So if we go to the next slide, Tom, we can see that we have soil moisture in this case. And so I've got this again just to show you that interaction between the atmosphere and the land surface. You can see as the cloud cover comes through, the soil moisture increases. We can see the water bodies start to fill up. And then as that cloud goes away and the temperature rises, the soil moisture dries out again. So that's just really to show you the sorts of output that we are dealing with. And then in the Atlas, we had to try and summarise all of that information and all of that detail into something that was useful to you. So if we go to the next slide, Tom, this is again just another list of the indices that we decided on, with the focus often generally on the growing season temperature rather than annual temperature, for example, or annual rainfall, because the feedback we got was that was the index that was of most interest. We also had a lot of interest in looking at heat extremes, so how long heat waves might occur, what number of days you might exceed temperature thresholds. And we also looked at some newer indices such as frequency of days with high human heat stress, where you might start to wonder about working outside. So Tom's going to go into a lot more detail about that as we go through. If we go to the next slide, thanks, Tom. So here we've got a representation of the different emission scenarios. So the Atlas is based on RCP 8.5, which is a high emission scenario. And as I said earlier, it is the scenario that we're currently tracking slightly above. You can see that there's a range in climate models within each of those scenarios. So here in the red, you've got that spaghetti diagram shows that that you do get a range in plausible futures, even following the same scenario. So the Atlas presents just the RCP 8.5, and the reason, and I guess another way that you can do it is by presenting different types of, a high and a low scenario. We chose to just give you the RCP 8.5 for a couple of reasons. One is that we have a certain amount of warming already committed into the climate system, so that even if global net emissions were to fall to 0 tomorrow, we still have some committed warming. That means we will have to adapt in the next couple of decades to temperatures that will continue to rise regardless of the emissions scenario. You can see in that bottom graph that the very low scenario and the high scenario, the purple and the orange, don't really actually start to diverge entirely until after 2040 or 2050. So so we know that we are, and we know that we have to adapt to a certain amount in the next couple of decades. If we did achieve a lower pathway, so for example, if we did actually start to achieve the Paris goals of limiting warming to less than 2 degrees, or hopefully less than 1.5 degrees, the data in the atlas is still useful because the same patterns will be observed, just at a lower magnitude and rate of change. Another thing we've done on the time series graphs that you will have seen, and Tom's going to give us more detail on, is shown how we can separate out the emissions from the time scale by relating it to actual policy targets of 1 degree, 2 degree, 3 degree and 4 degrees of global temperature warming. So it's also really important to remember that the projections are not predictions of future climates. They're just descriptions of possible future climates under different emissions scenarios. And we talk about a lot of these things on a global scale, but we know that actually these things are the impacts that we're seeing right now. We're seeing them on the ground and we're seeing them in our own regions. We know that we've been seeing increased droughts, storms, hurricanes, heat waves, bushfires. We've been seeing those not just in Australia, but around the world. And we know that these sorts of extreme events are expected to continue accelerating into the future. So one of the things that I think is really important in the Atlas is to acknowledge the fact that climate change is already occurring. This is no longer a thing of the future that we can put off and just say it's something that my grandchildren have to worry about. So what we've got here is some maps that show those changes that we've already seen. So then the top we've got growing season temperature, where you can see that there's a range in temperatures that have increased since the historical period, which we've got as 1961 to 1990, and the current period, which is 1997 to 2017. So you can see in some regions they've already had an increase in growing season temperature of about 0.8 degrees Celsius, and in others, particularly those with a maritime influence, like southwestern Western Australia and parts of Tasmania, they've experienced only 0.4 degrees since the historical period. And when I say only, it doesn't seem like so much, but actually it has been enough that we are fundamentally seeing changing weather patterns and much greater extremes. In the bottom corner, we've got growing season temperature, the changes in growing season rainfall that we've already experienced, again, between those same periods, the current period and the historical. And you can see with rainfall, as you'd expect, it's much more variable. There are places across the country which have had drying since that time, and others where they've had a slight increase in rainfall. And this, again, is because of those regional patterns that you see across such a big country like Australia, but also because rainfall is so naturally variable. And we're not actually really expecting that the trend caused by climate change to emerge from the background variability for another couple of decades, actually. So, Tom, I think that's over to you.
Thanks, Beck. So I'm going to take you for a bit of a tour across each of these different pages that we've got across within the Atlas for each region. However, I'm going to take a bit of a tour through the South Australian Central Cluster. Here we're starting with southern, I always pronounce this incorrectly, apologies, Fleurieu. And just this is the infographic page. It's a summary for those that aren't necessarily interested in the technical detail and just want to know about the general trends. Here we can see for this region, we've got not really that much change in rainfall. In fact, there's in the midterm, it's kind of suggesting a very slight increase, but you can see that these numbers are very similar to each other. Temperature, we've got a very sustained increase in temperature into the future with 2.5 degrees by the end of century following that high emissions scenario. For this region, frost is not a risk. It might be a risk in very small pockets, but as a rule, it's not something that's really a big risk for this region. Some of it, other places, for example, have 10 days a year or 20 days a year, for example. So, in this context, it's not there. Extreme heat measured as mean excess heat factor. I'll talk to that later. Big risk for this region. Again, with values like 19, for example, other regions around the country have values that are down at sort of like 5 or 6 for this particular index. So this is really, it's a big risk now, and it's an increasing risk into the future with the intensity of heat waves. And then aridity, so this is evaporation, rainfall divided by evaporation. And this sort of indicates that lower values indicate a more arid environment. And this is an increasing challenge for this region into the future. And we've got these pages for every region across the country. So if we dive in now for temperature, we're starting with the Adelaide Hills. The first figure, figure 1 up here, is what the observed mean growing season temperature is for this region based on the Bureau of Meteorology high resolution gridded data products. We can see that we've got a growing season temperature that is quite diverse across this space, ranging from sort of 20 down to about 16, depending on where you are. But across this region, if we move over to figure 2, there has been a fairly standard warming trend across the entire region. There isn't a lot of variability there. And this is what we expect to see from temperature. It's a broad scale feature operating at kind of quite large scales, almost continental in the way that it changes in that way. When we then look into the future, and of course these are all projections, figure 3 here, it shows that the spatial variability across the Adelaide Hills is going to be maintained, but the general growing season temperatures you should expect are going to gradually increase to the point where, say, the growing season temperature in this sort of cooler zone here is going to be warmer than some of the warmest regions across the warmest locations across this region as we move into the future following that highest emissions scenario that we do hope humanity can avoid. We can also present this information in a time series, and this is where for each particular point in time we plot every single grid cell on this plot, which creates that diversity. But this also is presenting all of the variability presented by the 6 different climate models. And so we've got a sort of 2 lots of variability here, the spatial and the different assumptions from different climate models. And what we can see for this region is actually they cluster quite well. So the models are all kind of telling us the same story across the space. We might be seeing some particular models in particular years have a cooler, some are warmer than others, but we're still seeing that kind of, it's actually quite clustered, particularly when you compare that to other regions around Australia. Each individual point is following a bit of a time series, and this is what we've got here with these example locations of what's considered a warmer location or a colder location across this space. These were defined as the 80th and the 20th percentiles, as defined in that spatial variability. And we can see that there's interannual variability that we're observing all through the time series. And for this particular region, it's indicating that we're starting to diverge from the historical climate, possibly as early as 2000, but definitely we are kind of really transitioning to a fundamentally different climate by 2020 as we progress. And so this region is quite sensitive to the earlier stages of climate change. In this plot, we've also got sort of baseline, these are the mean conditions for each of these locations. So each of these also has a kind of a halo of points around it, but it's just the mean kind of growing season temperature for Tasmanian East Coast, for example. And we can see here that in the Adelaide Hills, they kind of range in sort of those mean conditions that they see from Yarra Valley all the way up to Geograph, depending on your location. Just highlighting that kind of amount of variability that you see through this particular GI. We've also got presented here these different, as Beck said, these policy relevant, international global policy relevant zones. So this light yellow zone here represents when the global climate is expected to have increased by about 1 degree, which is more or less from now for the next sort of 20 to 30 years. And what that allows us to do is that if these are conditions that we stabilize our climate at, we can look at those and say, right, well, here's what we should expect to see. There is a transitional kind of phase, but we might be seeing quite warm years, well above what we kind of historically would have expected to see. And then those cooler conditions are really expected to become extinct over the coming sort of mid-term, or what we call the mid-term in the climate science community. In a similar way, we can use this greater than 2 degrees, 3 degrees, or 4 degrees. If climate change accelerates and the models have underestimated the rate of change that the climate's going to undergo, then we might need to sort of understand what these conditions mean for wine growing in a particular region, and what kind of adaptation responses are required in that kind of condition if that, say, starts pushing forwards and occurring earlier. And so that's what these different coloured zones here are sort of intended to be used for. It allows the user to think about things in terms of climate, in terms of the actual changes to the climate, as opposed to thinking about it in terms of a time series, and so grouping things in that way. Moving down to figure 5, we can also represent this information as like 20-year time periods that summarize all of that information into a single curve, and these are called probability distribution functions. I use these a bit throughout the atlas. What these are, it sounds like a big scary name for those that don't like statistics, but all it is we take all of the values of growing season temperature that have occurred across the entire multi-model range, so 6 models of 20 years, and then we count how often a particular value occurs. And in this particular context, this value of about 17 is the most common value, but across that space you still have places that are 15 degrees rarely in colder years, and other places that are sort of getting growing season temperatures of 20 degrees in those warmer years. And so we kind of get to see the frequency of that. Now, what this allows us to do is to see what happens to these conditions into the future. And so we can see this gradual marching forward of growing season temperatures that should be expected in this region into the future, with significant changes expected, or even just in the immediate term into the 2020 to 2040, and then but that's sort of resulting in sort of kind of looking a lot more like geograph over in Western Australia by 2060 to 2080, and then exceeding that following that higher emissions scenario. We can also look at that in terms of growing degree days. You'll note that some of these growing degree day values might look a little bit different to what you're familiar with, and I'll talk to that in a moment. But the growing degree days, you can also see that these are actually potentially changing shape a bit, with there being kind of a lower frequency here, meaning that there's more variability between seasons into the future of this particular variable as we progress into the future. And again, we've got these similar kind of zones that describe how other regions are presented or in this space, so that users can sort of get a bit of a sense of who they're becoming more similar to with relation to these particular variables into the future. Now, growing degree days. Growing degree days is typically measured from October to April, and a values greater than 10 degrees. Average daily temperatures greater than 10 degrees. However, what users wanted from us was a change in when the harvest date was going to occur into the future, or particular phenological thresholds that was when they were going to happen into the future. Now, obviously, you harvest different varieties at different times of year. They have different phenological moments at different times of year, and so it was not. Nobody really wanted us to say, well, this is what will happen to Shiraz, or this is what will happen to Chardonnay. They wanted something that was a little bit more generalized that they could use across multiple varieties. Now, if we want to get when the harvest date is going to occur, what we need to capture the changes across the entire season. And what we see here is that into the future, a lot of that additional heat that's being added to the system is actually being added prior to October. So we needed to build a system that accounted for that. So the growing degree days value had to be from July to June at least. We then noticed that those sort of aggregated values that were only July to June greater than 10 degrees were kind of resulting in very strong S-shaped characteristics. And most people that we engaged with, and what the literature states is that it isn't really very S-shaped in the way that the vines respond. They respond to much lower temperatures earlier in the season, most varietals. And so what we did is we used some of the literature from Moncur to develop thresholds at which we'd take lower average temperatures and incorporate those into the growing degree days calculation for that earlier part of the season. And this was a much better representation of how those many of the varieties respond. And the details of that are in the background material in the atlas. Now, this has resulted in much sort of straighter growth curves, which is what many of the people we engaged with felt was a little bit more representative. But what that does is it means that these values are not directly relatable to the growing degree day values you might be familiar with. And we've got lookup tables that you can use in the background material to get a bit of a sense of what's comparable. Obviously, if you start from 0 here, then making it comparable to something that starts in July is really difficult. And that's why we've produced these thresholds of 1,000, 2,000 and 3,000 as is required in these out years, so that you can directly relate, well, if you know that particular phenological features occur in December in your region, well, that's going to be the equivalent to a value of about 1,000 following this particular method. And by the end of century, that's going to move out to be sort of a month earlier. And that's what most of these thresholds have been able to find. And for this particular region, it is sort of moving forward, by about sort of 6 weeks by the end of century for particular thresholds, 4 to 6 weeks for this region. It gets a bit wiggly at this end because for this current period of 2000 to 2020, remembering these are projections, it's very rare for this particular region to reach values of 2,500, and therefore it kind of results in these kind of wonky curves that then become cleaner as the frequency of those events increases into the future. So moving around the region now and looking at McLaren Vale, starting with figure 1, we have this observed mean growing season rainfall across the region. There's some obvious influence here of some topographical features through the region. And what we can see is that there's been a gradual drying of this landscape, particularly at these sort of, higher elevations. But there's been a gradual drying that has been observed over this region of sort of 5 to 10%, depending on where you are. However, into the future, that the projections here, I mean, this is probably one of the more this is one of the stronger trends in regions across the country, where you can see that there is this sort of gradual drying in these figures here, but you can see that it's not dramatic. There isn't a big shift of going from blue to yellow, for example, in this range in figure 3. But there is definitely a drying feature, sort of going from those darker blues to those lighter blues, or the darker greens to sort of the lighter greens, depending on where you sit across that space. Once again, we can present this as a time series, and the really important thing to get out of this is that growing season rainfall is highly variable now, and it is going to be highly variable all the way to the end of century. There might be a slight decrease in the average growing season temperature, but growing season rainfall, but that is very, very slight, to the point where it's mostly just the same. There is very limited changes in that growing season in terms of the timing or the volume of rainfall that we should be expecting to see into the future. However, if we look at that non-growing season rainfall, that May to September period, there has already been quite a strong drying trend in that historical observations, and then in that historical period, and that is projected to dramatically accelerate even as of 2020, with this is some of the strongest drying trends that we see across the country for this particular region. So and as you can see, these trends are still actually quite slight in comparison to, say, the temperature trends that we're seeing. However, this trend here is quite it's one, you can see it by eye, and that's not true for a whole bunch of other regions across the country. So that's an important feature to note, that there is going to be an increasing sort of water demand or decreasing water availability for this region into the future. I'll talk more to that on the next slide as well. These plots in figure 6 are called violin plots, and these are just a probability distribution that is mirrored on both sides of this plot to sort of really highlight where the most likely conditions are, but also demonstrate the expected range. So in this particular example, getting no rainfall years in July are very unlikely, and they could be quite high rainfall July months in some conditions, although that's quite rare to get it that high. It's really going to sit more around that kind of, 90 to 100 mils per month, or for a July, and that's what these represent. We tested these with a number of people that said they really didn't like box plots because they didn't really reflect the variability that they saw within a particular region, month for their region, whereas this tries to capture that a lot better. Now, we've shadowed these current condition, these 2000 to 2020 violin plots underneath all of the other future areas, future periods. And we can see that allows us to see the changes. And this one in 2080 to 2100 is probably one of the easier ones to see, this one, or the 2060 to 2080 period. We can see that there's a dramatic drying in July where there's a decrease in the sort of typical conditions that you'd expect to find in that month. There's also a decrease in the frequency of those wet years and that's also true for August and September, and also June and May. So we see that across that whole kind of May to September period, there's a decrease across all the months. We can present this information again in figure 7 as probability distribution functions, which can show the changes expected in particular seasons. And we can see that there is already underway a drying trend in the next period to come, this 2020 to 2040 period, which just sort of gradually accelerates as we go towards the end of century. And this is true across the winter and spring periods, and also across that autumn period, although that's a far more dramatic change as of 2040 to 2060 than it is in the immediate term. Noted here, summer is not really experiencing that much in the way of change, even out to the end of century. It's really all in those wetter months that those particular features are observable. If we use those sort of phenological thresholds that we got out of the growing degree day calculation and try and estimate the number of rainy days during the 2-week period surrounding these particular phenological thresholds, we can see how they change into the future. And the most dramatic changes are really at those higher phenological thresholds as they move out of being in that sort of May-June period and move more into being achieved by March or April. And so that's really what this is telling us, is that they might be quite wet at the moment, and possibly not even relevant to growers at the moment, because you've already picked everything by that time. But these particular thresholds then move into the those drier months, and thus become there's less rainy days when those features are reached. At those lower phenological thresholds, you can see there's not really much of a change, maybe an edging sort of getting slightly more rainy days, but we're not talking about significant changes here. They're like, half a day, if that, into the future. So no big changes to worry about in that context. Sticking with McLaren Vale now to really kind of highlight the importance of the combination of moisture changes and increased temperature changes, we've got aridity here. And we can see the observed aridity in figure 1, relatively kind of consistent across the landscape, although these colour scale does make it difficult to see the actual importance of the changes of these kind of, wetter zones versus the drier zones. And we can also see that how has this changed over the last period? Well, it's complicated. It says here that the sort of more northerly parts of McLaren Vale have experienced a drying trend, very slight, but still, whereas the southern areas have seen more of a kind of, an increase in moisture availability. And that's what has been observed from the observational records. Into the future, there is a gradual drying trend here that as we can see, we get kind of more orange, going from yellow to more orange in the past, and those spatial features are maintained into the future, as is expected, as they're mostly driven by those topographical components. If we look at the projected aridity index, and as I mentioned, the McLaren Vale is one of the regions where the trend has possibly started earlier than it has in many other regions across the country. And that possibly is why some of the region has been proactive in developing sort of new water supply mechanisms throughout the region. But this increasing or the decreasing aridity index is indicating a more arid environment. It's much drier, and this is quite a dramatic change that is going to take really sort of start to kick off from about 2020 onwards, which is and really kind of moving away from any of those really wet years occurring, and far more of those really dry years occurring across the entire landscape. And these are much easier to see the months in which those drying trends are going to occur, and the magnitude of those changes as we look at how the violin plots change into the future. This similar trend is also represented in when we assess the sort of the average aridity index across the various seasonal periods, and we can just see that in every month, every season except for summer, there is a really quite dramatic increase in these aridity values, and that's even more obvious when we look at what the mean aridity index was from July until those phenological thresholds were reached. And we can see that there's a big shift that we're expecting to see as in the 2020 to 2040 period for each of those particular thresholds, regardless of whether you care about that drying happening at your flowering stage or if it's at that sort of harvest stage, depending on exactly what time of the year is important to your varietal. Now here, I think it's important to mention, it was a question that was sent forward and asked prior to the webinar, is does this consider the water supplies coming through the Murray-Darling Basin? The short answer is no. This is only looking at rainfall falling onto the landscape. But as you can see with these particular trends, the demand for water across this landscape is going to significantly increase, and the Murray-Darling and that means that there's going to be increased competition for water from wine grapes versus other produce or primary industry into the future. There is work being done by CSIRO, and it has been underway for some time, and they have multiple reports working with the Murray-Darling Basin to really look at future changes into the water supplies down that system. But it must be noted that it's really an extraction problem that is driving most of the issues in the Murray-Darling, rather than significant changes to water supplies, although this is something that does need to be given a lot more thought and a lot more dedicated study in the immediate sort of the next 20 to 30 years in terms of really understanding what those changes are going to look like and the impact that's going to have on water availability through these regions. I strongly recommend chasing up the CSIRO reports that have been written if you're interested in understanding the challenges being faced in that space. Moving now to Langhorne Creek. Here we're showing the extremes of heat, and we've got this excess heat factor and what's been observed over this space. As you can see, there isn't a large number of points across this region. It's quite small, and that is reflected in the data points that there's this blockiness that you can see across the region. There's a lot of consistency across this zone, and we've seen a gradual increase in the excess heat factor across this region, with slightly higher increases in the southern part rather than compared to the northern part, but really the whole region's experiencing the same kind of trend. Into the future, there is a gradual increase in these excess heat factor values, and this is important to keep in mind and to recognise as we move forward. Now, what is excess heat factor? Excess heat factor is a value that's reported by the Bureau of Meteorology, developed by BOM and CSIRO, to be able to compare the relative intensity of heat waves across time and space. So the intensity of a heat wave that you might experience at Langhorne Creek at the same time as that event is being experienced, say, in the Barossa Valley, really depends on what the residents of that region are familiar with or acclimatized to, and that's what this excess heat factor takes into account. Takes into account those previous 30 years of temperature, what people are expected to be able to manage. And it crucially also takes into account overnight temperatures. And so if we move from this sort of figures 1, 2, and 3 down to figure 7, we can see that these overnight temperatures are represented here. It shows that how those temperatures are expected to change into the future. We've got a bit of an increase in overnight temperatures in the immediate term, but really sort of the big changes are sort of not expected to happen until 2060 to 2080 or even 2080 in those overnight temperatures. In contrast, the daily temperatures, the daily maximum temperatures that experienced during a heat wave are already on the march. They're already moving forward with sort of more or less sustained increases in those daily maximums experienced during a heat wave all the way out until 2080. The timing of those heat waves is not really expected to change too much, and that's partly because these excess heat factor calculations take into account the previous 30 years of data. And therefore, as the previous 30 years of data increases, as climate changes, then the values that you need to reach in order to be considered a heat wave following this calculation increase as well. And so we typically get the heat waves occurring sort of over those warmer months. That's why it was really important to also take into account the extreme temperatures themselves and the frequency of those. And that's another way of assessing that extreme heat influence on, say, a grape, which can't go hide inside in an air-conditioned room when these particular events happen. And so at the moment, we can see already that there's, say, about 30 to 40 days a year in Langhorne Creek that we're expecting to see greater than 30 degrees. And this is going to start to really increase into basically from about the 2020 onwards, to the point where we're sort of edging towards 60 days per year. So, a 30% increase, 50 to 30% increase over the coming years in the frequency of those warmer days. And that's also being followed by these extremely hot days with greater than 35 or greater than 40 degree temperatures, really kind of increasing in their frequency. And with these really kind of quite extreme temperatures really starting to emerge as those really extreme days. For those of you that like percentiles and really like statistics, we've also presented this kind of frequency of occurrence in the percentile context. So you can see sort of, and the way to think about these for those that are less familiar with percentiles is the 99th percentile is the top 4 hottest days of the year. And so those are kind of, relatively stable in the immediate term, and then sort of with much sort of more extremes expected to really start being more obvious in that 2040s onwards period. In comparison, those kind of like typical warm days, which is the top 30 days or thereabouts for the 90th percentile, is they're actually going to increase a little bit faster for this region than those top end extremes. It was also recognised that how humidity can influence how hot it feels on a particular day is important. And in Langhorne Creek, we already have a couple of days a year where humidity makes it really difficult to work outside, and this is projected to increase slightly with as an increasing risk into the future. But really, this region's quite dry, and there isn't really a high frequency of hot conditions and moist, humid conditions across this landscape, and that's why you can be working outside in quite hot conditions in these climates because of that lack of humidity. For extreme cold, many of the regions across here don't really have a big risk of extreme cold. There are isolated pockets across the Adelaide Hills, somewhat represented here by this increasing frequency at this sort of relatively coarse scale when you're talking about frost conditions in such a highly topographically varied environment. But it does sort of indicate where those frosts are kind of more likely to occur. But basically it's saying that the frost risk has been decreasing in most of those locations. You'll note here that the observed conditions have said that there's been a relatively minor increase, and that has been driven to an increase in the frequency of clear sky nights into the future. That's all indications seem to be saying that's really what's been driving that. And those clear sky nights, although they do increase into the future, the minimum temperatures that we're seeing overnight are projected to increase to the point where that's more of a transitional risk over the next 20 years, whereas by the end of century, or by sort of that 2040 period, those clear sky nights do exist, but they don't result in frosts in anywhere near the same frequency as what we're really observing now. And that's it's a transitional risk that's happening across particularly the South Australian and sort of Western district of Victoria, that where those observations have been occurring. And across all of these kind of cold condition metrics, be they monthly minimum conditions or the number of actual frost risk days for each month into the season, there's just this very consistent decrease across that entire landscape and entire sort of time period, to the point where it is becoming such a modest, minimal risk into the future that it's not something that is going to need to be considered at all in some locations from now onwards. So that's a little traverse across some of the sort of key regions that I was asked to present against for the South Australian Central Cluster. Inside the atlas, as Beck mentioned earlier, it's really important to kind of present this information in this national context so that an individual location can identify where it might be more similar to across this national environment and make linkages, either professional or just as an interest of looking at how various different conditions could be managed in different ways, and just pointing out those sort of locations most likely to be similar to you, either ranked in that sort of like current period of where you sit across that spectrum, or across the sort of that rigidity changes. We've got that for a handful of variables at the beginning of the atlas. So when we look at this idea of being able to find analogues and looking for who are you similar to today and who are you going to be most similar to into the future, we can then come up with ways of making those comparisons on a single variable kind of conceptual space. But we can also do it on a multivariate approach, and this is using two of them, the growing year aridity index versus the mean growing season temperature. And for the areas that are important to the South Australian Central Cluster are highlighted in blue here, surrounded by those other regions from around the country. With those, if anyone's from Kangaroo Island, you're sort of hidden away in there. And we can see that there's these kind of pathways that each of these locations are following. So I'll talk first to the Adelaide Hills. It's sort of sitting by itself and easier to see. We've got this quite, strong warming trend that's been happening in the Adelaide Hills, but that drying trend hasn't really started to kick in this location just yet. Whereas it's expected to really kick in the coming sort of 20 years, where that's going to be one of the dominant driving factors in the Adelaide Hills. And as it proceeds along its sort of projected pathway, it will start becoming a little bit more like, say, Goulburn Valley or Cowra, but as it projects, travels through this landscape out to 2100. In a similar way, we've got some McLaren Vale has sort of in some parts of it looks like it's actually sort of slightly decreased, had an increase in moisture, but then that trend is really going to sort of reverse, and it's going to traverse this pathway up to here, sort of maybe more similar to the Adelaide Plains, for example. Langhorne Creek has had, it's already quite dry. It's had almost only a warming trend with almost no change in its aridity at all over this past 20, 30-year period. But then that's, again, projected to sort of start drying and then transition out to being a little bit more like the Southern Flinders Ranges or maybe the Shoalhaven Coast. Sorry, not Shoalhaven Coast, the Swan Hill region as it transitions out towards 2100. And so this allows people working in those regions to look at, like, well, who are they going to become more similar to? What are the kinds of varietals that might be more appropriate for that? What are the types of management strategies that they have to implement as a standard approach to growing grapes in those regions? And therefore, and what are the sort of best marketing strategies that you might want to implement if you're following this kind of trajectory, and therefore the style of wine that you make might have to change, or even the varietals that are most profitable might need to be reassessed. And so I'll hand back over to Beck and have a drink.
Thanks, Tom. That's a whole lot of talking, but there's a whole lot of detail in there that needs explaining. I guess just really quickly, one of the things I didn't say at the beginning was that if you're interested in understanding more about the general climate science and how we know that climate change is happening and how we know that it is caused by human activity, in the first and second webinars, we spent a bit of time at the beginning going through that. So if you're interested in that, then you should be able to access those recordings through the Wine Australia website. But just as a really quick summary, because we're running out of time, I think we just, to make the point that we know that change is already occurring, that we've presented those observed changes, and we know that those changes are projected to continue and to accelerate in many cases. So there's a lot of variability across Australia. It's a big continent, highly variable naturally, but there are consistent trends that we see in all regions, and that's that strong warming trend that we see getting stronger as the century progresses. We see increases in annual temperature and as well as growing season temperature. Increased aridity is consistent across all regions as evaporation generally increases under warmer temperatures. Fewer growing season frost risk, more intense heat waves, and substantial increases in excess heat factor in many regions. So we know that adaptation is going to be needed, and that means we need to access this sort of climate information to help plan for the future at different timescales. So things to think about for the next decade, the next 20 years, going up to middle of the century and at the end of the century. I just wanted to really quickly thank our research partners, Peter Heyman, Paul Petrie, Dane Thomas from SARDI, Fiona Kerslake from TR, Tasmanian Institute of Agriculture, and the modelling team at CSIRO. But in particular, thanks to the wine growers across Australia, particularly in our case study regions that we worked closely with to try and make sure that this climate information is useful to you and can help support you going into the future. And also thank you, obviously, to Wine Australia for funding the project. Thanks very much.
Thanks very much, Tom and Beck, for that fantastic presentation. There's always something new to learn. And thanks for sticking with us, everyone. We do have a literal panic button at this end, and it's good to know that it works. So well done, SA Central. You've had the full breadth of experience with us here today. If you're leaving us now, please link through to the survey in the chat function. We'd love to hear what you think about this webinar and how we could potentially improve our offering in the future. If you have any questions, it's not too late. Please flick them through to us. I think, given the start we had, we'll cover off on a couple of questions. So if people want to stick around, that's fantastic. Otherwise, as we said before, the presentation will be available on the Wine Australia website. So we have had. Actually, I was going to ask a question about Adelaide Hills in particular. So Adelaide Hills is one of the more unique regions in that it is a large region with a lot of different geographical pockets and a lot of variability across the region. Do you think that the Atlas is still useful for a region like Adelaide Hills?
Oh, absolutely. So, sorry, Beck, I'll take this one. Yeah, absolutely. So the information that's projected at the moment is, and also is observed at the moment, is always going to have to be at an aggregated scale, unless, can you hear me? Oh, okay. At an aggregated scale. And so therefore, like, it's always going to be useful. It's just that, say, if you know that your location is 3 degrees cooler than what's projected or what's in the Atlas, then that condition is just going to be shifted, or it's going to be sitting at those kind of cooler parts that are projected in the Atlas. And so but those trends are all going to be very consistent, and that's what we're seeing across these landscapes, and even in regions where there's very large variability captured within the model projections. And for those that are interested, have a look at either the Tasmanian or the Alpine Valleys areas to see just how variable it can get across a region, and how that information is captured and what it looks like. So I think the Atlas is absolutely going to be telling you, here is the direction of change, and here is the magnitude of that change relevant to this region. But there are going to, particularly Adelaide Hills, there are little pockets that are significantly cooler than some of those lower elevation regions. And when you aggregate anything up to sort of a 5 kilometre grid, you do lose some of that variability.
We have had a question come through on the varietals, and whether there's a body of work in progress or plan to better understand how we pivot to grape varieties that are better suited to the forecast climate changes. It's a good question.
So the short answer is we are not connected to any work at the moment in that varietal space, although we'd be very interested to work in that space. But there are groups around Australia, the CSIRO, and also some of the big grape propagation companies, like is it Chambers? But out near Heathcote. They've been doing work in these alternate varieties for a very long time, and there are lots of different opportunities out there. However, that specific effort of actually saying, in this location, given these changes, what is the appropriate varietals for us to select? I'm not sure how progressed any effort in that space has come, and I think that's the next obvious big piece of work to do.
Can I just add to that, Tom? I think obviously there are many hundreds of and thousands of different varieties, and so a fairly obvious next step is to apply that analogue approach internationally, to have a look at who grows what varieties now into the future the warmer, drier conditions that we know are projected for many of our wine regions. But my feeling is that that sort of research into which is the most appropriate variety is going to be influenced by so many things, not just climate. Management techniques, markets, all of those sorts of things. So obviously climate is just one factor of that, but it should definitely be considered, I'd say, going forwards.
Yeah, I agree, and I think that the beauty of the analogue tool is that you can use that and say, okay, we're going to look more like Swan River, so go to Swan River and see what they're growing and how their varieties cope with the conditions that are there, and that would be a good starting point possibly. So I think we might close things up for today. So that brings us to the conclusion of today's webinar. Next steps are that you'll receive an email with a link through to the recording and also to the survey if you missed it today. The recording will also be available on our website, as I mentioned earlier. And there you will also find links to the ABC Landline story, which kicked off the launch of the Atlas a couple of months ago. The final report for the Climate Futures Project, which gave rise to the Atlas, and the Climate Atlas itself, where you can download the whole thing if you wish, or you can also download your specific regions of interest. And we've posted most of those links through to the chat page also. So I really hope this has given you an insight into what the Climate Atlas contains and how to extract information from it, and hopefully that can empower you to move forward, to start to adapt to what's going on in your region. And please feel free to reach out to Wine Australia if you'd like us to be part of those ongoing discussions and you'd like any assistance at all. So thank you very much, Tom and Beck, for a fantastic presentation. And I think that concludes for today. Thanks, everyone.
Thanks, Sharon. Thanks, everyone.
See ya.
Bye.